Oke, saya Roy. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Good morning, everyone. See you again. My name is Zaki, and I'm here with Mas Adi Sudrajat. And today we will um, learn and talk about the introduction to cryptography. Actually, uh, this is the like sharing session from the Chimpa School. The July, I think. The cryptography in the Simba school, there are two lecturers, Professor Indah Emilia Wijayanti and Dr. Ani Monalifa. And here I will um, sum the lecture of both uh, Bu Indah and Bu Ani. And in the exercise session will be conducted by Mas Adi Sudrajat. Okay, I think he still join the still not join. Okay, in here I will talk about the introduction to cryptography. So it's very basic principle of cryptography. I will start about the communication and then early cryptography and then uh, some basic number theory and then classical cryptography and then introduction to public key cryptography, which is a development key exchange, and then the RSA crypto system, and then the El-Gamal crypto system, and elliptic curve crypto system. I think all of you is already know about the cryptography and some um lecture before before today. I think it's about elliptic curve and analytic number theory. So some of you maybe is already know about the notion. Okay, I will start with the communication. So we are as a human every day we communicate to each other by many communication channel. In the past we use like a telegraph to communicate to another people, especially when we are in the long distance communication. And then we already know about the telephone and then the cellular network. We use it every day. And we also use mobile phone. Every day we use it to communicate to another people. And the communication channel that we are using to now is the internet. Our computer, our smartphone is connected to the internet to communicate to another. But uh, the internet, the telephone, and many communication channel have thread, the communication thread. We can hear that the internet is a open communication channel, so everyone can read, can see what we send. Okay, it's very easy. So we have a issue about the security threat that the internet, mobile network, it cannot be sure that that is secure. Yeah, someone maybe is can see, can read our message. Someone who is dropping, someone who checks our message, then someone who theft our identity. So some of the security threat, especially in the aspect of confidentiality, then one of the solution is we use cryptography. So the story of cryptography is uh, when we read the historical book about the cryptography, then the first one that uh, the first one that we know in the story is the Caesar cipher or Civ cipher from the ancient Greek. They shift the letters to another letters by shifting. For example, if we use three shift, then A become D, B become E, C becomes F, T become G, and X become A, Y become B, and Z become C. So using three shift, a message cryptography becomes like a scrambled word. FUBSWRGUDSK and B. So from the meaningful message becomes a scrambled message. Okay. So what is cryptography? Cryptography is a study of mathematical techniques related to aspects of information security, such as confidentiality, data integrity, and so on. Okay. In terms of confidentiality aspect, we use encryption and decryption process. What is encryption? Encryption is a process of converting a readable message or meaningful message or a plain text into a scrambled message or a code that is untangible, or we call it the ciphertext. And what is the decryption? Decryption is the reverse of the encryption to to convert the ciphertext into the original message or plain text. And the encryption and decryption process use some method or algorithm, we call it cipher, and a secret parameter that we call it a key or a secret key or a private key. Here we use some basic terms that we use Alice and Bob. The first party is Alice and the second party is Bob. And we also introduce if. If is a third party here. Uh, I think if is she, right? So if is a eavesdrop, everything that Alice and Bob share using the communication channel. And if it's an attacker here, so if wants to know what is the secret message between Alice and Bob. And in here, we use the Kirchhoff principle that cryptographic algorithms are public and the key are kept secrets. So everyone know the algorithm on the cipher that Alice and Bob use. And here's uh, the figure between Alice, Bob, and Eve. And Eve is in the middle. Okay. So Eve only knows the the algorithm, the cipher, and the ciphertext. This is the reason why we use encryption like this. And now I introduce cryptanalysis. It is the set of the cryptography. That is, cryptanalysis is the science of studying how to obtain secret keys without knowing the key. In general, cryptanalysis is the science of studying mathematical techniques to break cryptographic techniques to obtain secret messages. And cryptology is the science that studies cryptography and also cryptanalysis. Yeah. And before we start some crypto system and or cipher, we recall some basic number theories that I think that you already know that we have here is Bezo's theorem. So we have, if we have the GCD of two non-zero integers a and b, then there exists two integers s and t, such that as plus bt is the GCD of a and b. And we also, I think we also already know that we can compute the GCD of two integers using the Euclidean algorithm. This is the example of Euclidean algorithm. And we will compute the GCD of 154. We only compute the sum division algorithm. It is very simple. The GCD is 2. And we also uh, use the Euclidean algorithm to find the value of S and T in the Bezo's theorem. So the idea is just to reverse the Euclidean algorithm. Okay. And we can find the value of S and T. And then we use some congruences. Is the definition. I think you already know. And we also use multiplicative inverse. And we have a theorem that uh, an integer a is invertible modulo m if and only if the DCT of I and m is 1. So I and m are relatively primes. And we also know about the Fermat-Little theorems and also the AOP function. And, and we also know the Euler's theorem, which is very famous in number theory. And we also already know about the Chinese Riemann theorem. And in in the ring theory, we also have the same theorem like this. Okay, and we back to the cryptography. Okay, now we have a new concept about crypto system. So, what is crypto system? Or we also called it cipher. It is a set of procedures, of protocols, and algorithms, encryption and decryption. By Simpson in 2019, uh, he defined crypto system is a five tuple P, C, K, E, and D, where P is a finite set of plain text, and C is a finite of ciphertext, and K is the key space or the set of key of all the keys. And between the key, plain text, and the ciphertext, they hold this that uh, the decryption of encrypted encryption of X is must back to the original plain text X. Okay, this is the mathematical lesson about the Caesar cipher. So in the Caesar cipher, we use Z26 because uh, the letters in alphabet they are 26. So we use Z26, the group of integers modulo 26, and we use the correspondence between alphabet with the integer, A with 0, B with 1, and Z with 25. So in here we use the set of all plain text, the ciphertext, and the key space C26. And for the plain text X in Z26 and the key K in Z26, the equation function of the Caesar cipher is given by X plus K modulo 26. So it's very simple. So the shift operation is the addition with K. And for the decryption is very simple. So we just move backward. So if we have uh, a ciphertext Y, then the decryption is Y minus K. For the example, if we use K is the the key is 3, then the plain text cryptography is encrypted to FUB and so on. So I think it's very simple. So this is the exercise for you. to break this Caesar ciphertext. Okay. Okay. You just try all of the uh, possible keys. You can shift it with 1, 2, 3, 4 because this key space is very small. There are only 26 keys, and you can try all the possible keys and find the meaningful one. Okay, this is very simple. Okay, and then I'll introduce the beginner cipher. It's like a shift cipher or Caesar cipher, but with they're using blocks. Okay, blocks. Each block they encrypted using Caesar cipher. So each block they use different Caesar cipher, and here is uh, the encryption function. The plain text is a vector in Z26, the length of n, and the secret key is also a vector in Z26 of length n. And the decryption function is also very similar with the Caesar cipher. Okay, for the example here, the plain text mathematics is encrypted using a key crypto, and it's become like this. Okay, and I'll introduce the affine cipher. In affine cipher, we use uh, two operations here. We use the affine function ax plus b. So we use Z26 as a ring. So we use addition and multiplication modulo 26. And the equation function is affine function. So the secret key should be uh, two integers a and b. But in here, a must be invertible modulo 26. So the DCT of a and 26 is must be 1. Okay, and the decretion function of the affine cipher is given by the inverse of A is multiplied by y minus b modulo 26. So it's also very simple. And we also have the Hill cipher. Or in here, the accretion and decretion we use uh, matrix multiplication modulo 26. In here, the secret key is the matrices is a matrix, non-singular matrix of Z26, and the plain text is a vector in Z26 of length n, and the encryption function and decryption function is given like that. So this is also very simple. And actually, the Hill cipher is uh, in 1929. Someone in someone used it in military purpose, and uh, Actually, they are a machine that can compute a hill cipher. Yeah. Okay. So we know that uh, we have some cipher machine here that used in the World War One, I think, the First World War. And we also know a very famous cipher machine in the world. It is the Enigma machine. In the Second World War, they use substitution, permutation. Yeah, it's very complex. And then uh, the Caesar cipher, Ficino cipher, Hill cipher, uh, Enigma cipher, all of them use the same key to for encryption and decryption. So the crypto system that use the same key for encryption, we call it symmetric crypto system. So what is symmetric crypto system? It's a crypto system that use the same key for encryption and for decryption. There are many examples of symmetric crypto system. The example is Caesar cipher, the Hill cipher, the Fidelity cipher, Playful cipher, Enigma cipher. In the modern era, we already know the DES, the triple DS, the Blowfish, and the AES. Actually, AES or Randall cipher now become the standard of semantic cryptography since 2001. The AES use a series of multiplication, substitution, permutation on the matrix of the finite field, the GF to the 8. Okay, and then I will introduce the problem in symmetric cryptography. In symmetric crypto system, Alice and Bob must agree on the same key, the key for encryption and for decryption. What if Alice wants to send a secret message to Bob, but both of them cannot agree on the same secret key? This problem has been experienced in the use of semantic cryptography for thousands of years, since the Caesar cipher until I think the end of the world and the Second World War. So in 1926, uh, Whitfield Diffie and Martin Hellman published a paper that is very important in cryptography. The title of the paper is New Direction in Cryptography. So the Whitfield Diffie and Martin Hellman proposed a new method that allowed Alice and Bob to agree the same key for encryption and decryption, even though that they're using an insecure communication channel like the internet. So actually, Tiffy and Hellman, they use some hard problem in mathematics. It is the discrete logarithm problem. So this is the definition of the discrete logarithm problem. Let P be a prime number, and we already know that the P is a finite field. Then The ZP star or the ZP without zero is a cyclic group under the multiplication modulo P. Since the ZP star is a cyclic group, then the ZP star have a generator, or we call it the primitive root modulo P. So if we take an element X in ZP star, then there exists a positive integer A such that X is G power of A, and we can say that A is the logarithm of X with base G. The problem finding or computing the logarithm X with the base G is called the discrete logarithm problem, or DLP. And for a big prime, it is easy to compute X equal to G of A, but it is hard to compute the logarithm or to find the A if we just know the value of X and G. And the Diffie and Hellman used the DLP to construct a key exchange protocol. So here's the Diffie-Hellman key exchange protocol of a ZP star. Okay, in here, Alice and Bob agree a prime number P and a primitive root modulo P, that is G. The values of P and G are public, and here's the protocol. Alice choose an integer n, which is secret. Sorry, this is not n, but A. Should be A, sorry. Alice secretly choose an integer A and computes SA, and Alice sends SA to Bob, and Bob also secretly choose an integer B, and Bob computes SP, that is G to the power of P, and sends SP to Alice. So Alice have A and also SP, and Bob has SA and the value of P. So Alice compute SP to the power of A, and Bob computes SA to the power of B. And the magic happened that Alice and Bob successfully agree the same key. Yeah. And this is the proof that Alice and Bob have the same key. And after Alice and Bob agree on the same key, then they use the key to encrypt the message using symmetric crypto system. This is an example of the Diffie-Hellman key exchange. Okay, any questions? Okay. Uh, Now we will discuss about the security of the discrete logarithm problem of ZP star. So the attacker, it is if knows the values of P, the prime number P, the primitive root modulo P, that is G, the value of SA, the shared key, the Alice shared key, and SP, the Alice, the Bob's shared key. Okay. To obtain the secret key, or if can compute the discrete logarithm of SA or SP with the base of G. So the security level of the diffie-Hellman key exchange is same with the difficulty of solving the discrete logarithm problem. So to make the security of the diffie-Hellman key exchange is hard is to use we should use the big prime number. This is the an example of a big prime number. We use a 300 digits prime number. Is the example. Uh, there are some methods to compute the DLP, the discrete logarithm problem. The first one is Pollard rule method, and the second one is index calculus algorithm. But it is still takes a very long time. Even that you not have to try all possibility. Okay, but this is still very hard. And we can generalize the development key exchange by using a finite cyclic group generated by G, a finite cyclic group G. The the group in and a generator is public. Okay, and Alice security choose an integer n between 1 and the order of G and computes the SA, the G to the power of A, and sends the value of SA to Bob, and also Bob secretly choose an integer m between 1 and the order of G, and then compute the value as SP is G to the power of P modulo P and sends SP to Alice. And then Alice know the value of A and SP, and Alice compute the key A is equal to SP to the power of A, and Bob computes the KB, the SA to the power of B. Uh, Alice and Bob successfully agree the same key A is equal to KB. And we can change the cyclic group. We can choose the cyclic group with another cyclic group. We already know that if F is a finite fit, then F star, that is the set of all non-zero element in F, is a cyclic group. So we can construct a cyclic group using a finite field. And here we can use z p, where p is a prime, is an example of finite field. And also we also use the Galois field, or the finite field of order p to the power of m, which the construction is using the polynomial ring ZPX modulo fx, where fx is an irreducible polynomial of degree m in ZPX. And for the hardware implementation, for uh, practically used, we often use the binary finite field, or binary field z to x. Okay. Uh, Now, if we use the symmetric symmetric vector system, uh, we have these problems. In symmetric vector system, the encryption and the decryption use the same secret key. So if there are two parties, then there is one secret key. If there are three parties and there are three secret keys, if there are four parties, then there are six secret keys. So if there are n parties that communicating together secretly, then there are the combination of n and two secret keys that are used. It is the problem because if we if there are um, many parties that communicating together, and the key that they are used are very big. Okay, so this problem is solved by the three men. Uh, the name is Ron Rivers, Adi Samir, and Leonard Alderman in 1977. So Rivers, Samir, and Alderman published a paper that very important in the development of cryptography. The title of their paper is A Method for Obtaining Digital Signatures and Public Key Crypto System. So in that paper, they describe a method that can encrypt a message, a plain text, using a key that is public. So in here, we use the term the public key and the private key. So Rivers, Shamir, and Edelman, uh, they use a hard problem in mathematics, different with different element. If different element use the discrete logarithm problem, in here the Rivers, Shamir, and Edelman use uh, integer factorization problem. We already know from the number theory, from the fundamental theorem of arithmetic, that for every integer greater than 1, there exists a unique prime numbers P1, P2, PM such that A is the P1 multiplied P2 until PM. It is the factorization of A, and the factorization is unique. The problem of determining the prime factors of an integer is called the integer factorization problem. And reverse Samir and Edelman exploited that problem to construct a new encryption method called the RSA crypto system. It is the first public key crypto system. Here's the example uh, of very big integers. Actually, this big integers is a multiplication of two primes, P and Q, and we just want to know what is the value of P and Q, the two primes numbers. Until now, there is no someone who break to find this value of P and Q. Actually, this number is called the RSA 2048 because this this number is 2048 bits, and it's 617 digits. So here's the construction of the RSA visual system. So let P and Q be distinct primes numbers, and let N be the multiplication of P and Q, and let Zn be the ring of integers modulo N, and by the Cauchy-Riemann theorem, then Zn is isomorphic to Zp cross Zq. Okay, by the Cauchy-Riemann theorem. And let Zn star is the unit group of Zn under multiplication. So Zn star is the set of all element A in Zn such that the element is relatively prime with N. And the order of the group Zn star is the Euler function. And the order is Vn is actually P minus 1, Q minus 1. And for the Euler's theorem, we already know that if M is a non-zero element in Zn and the GCD of M and N is 1, that M to the power of Pn is 1 modulo N. Okay, any questions?
I think so far still
Okay,
clear.
okay, yeah, okay, and then uh, I'll introduce you the public key crypto system or asymmetric crypto system. Suppose that Alice wants to send a secret message or a plain text to Bob. Then The one who create a public key and private key is Bob. So Bob creates a pair of public key and private key. The public key are public. The public key is public, and the private key it should be only be known by Bob. So if Alice want to encrypt the plain text, then Alice use the public key from Bob. And Bob use the private key for decryption. Okay. And there are three processes. The first one is the key generation, and the second one is encryption, and the third one is decryption. The key generation uh, the key generation uh, is Bob, and encryption is for Alice, and decryption is Bob. It's for Bob. So when we use asymmetric crypto system, if there are n parties communicating separately, then we only use n keys. So it's fair. It is uh, okay. If there are n parties communicating together, then they are only use n keys that are needed. So each party has a public key that is used for encryption. So here is the RSA key generation. So if Alice want to send a secret message to Bob, then the first thing that Bob uh, choose two distinct prime numbers, P and Q, and then Bob computes the value of n, that is the multiplication of P and Q, and Bob also compute the Vn, the Euler P function, that is P minus 1, Q minus 1, and then Bob choose uh, two integers, E and D, such that E and T is E times T is 1 in modulo Vn. So in here, D is the inverse of E, or E is the inverse of D. And then Bob publish the public key. The key P is the pair N and E. And Bob keeps the private key, that is D. And after that, uh, Alice now knows the public key from Bob, that is N and E, and then Alice choose the plain text M in the end, and then Alice perform the encryption by computing M to the power of E modulo N. It's very simple, and then Alice sends the ciphertext to Bob, and after that, Bob receives the ciphertext C from Alice. And Bob already know the private key, that is D, and then Bob performs decryption by compute the C to the power of D modulo N. And the magic happen that the calculation that C to the power of D is equal to M, and And the proof of the decryption is given for the exercise. Okay, the security of RSA system is based on the difficulty of on integer factoring. So in here, the attacker, that is if, knows the public key, that is N and E, and also the ciphertext C. So if to obtain the private key, if computes the value of D, that is the inverse of A modulo Vn, but to to know the value of Vn, which that is P minus 1 times Q minus 1, if must know the value of the prime numbers P and Q. So, so the security level of the RSA system is equivalent to the difficulty of factoring the value of n. And we already know some factoring methods that are Pollard row method, Pollard P minus 1 algorithm, and also Dixon random sequence algorithm. But if we use a very big primes number, then this method is still uh, cannot break the RSA system. And we also introduced the digital signature. So in here, the digital signature is to solve another problem in communication security. If the RSA, the Cesar cipher, the DES, IS, the, they solve the confidentiality aspect, but the digital signature is solving the uh, authentication aspect. And in here, we also use the hash function. Hash function is like the fingerprint of a message. It can be used uh, to solve the integrity aspect. If we want to know a message is already changed while transferring or sending using an in-checker channel. So in the digital signature, the message is signed using the private key, and then after that, the receiver uh, can use the public key to check that the sent message it is true that the message is come from Alice. So Bob here as a receiver can check that the message is from the sender, that is Alice. And here is the RSA digital signature. So the process is only just the modification of the RSA crystal system. If in RSA crystal system, the encryption is used using the private key, but in digital signature, the signing the message is using the secret key. In here, Alice want to sign a message, so Alice choose uh, two distinct prime numbers P and Q, And Alice compute the value of n, that is pq, and also the value of the Vn, the LRP function, that is p minus 1, q minus 1. And then Alice choose two values, two integers a and b, and such that AP is congruent to 1 modulo Vn. Actually, A is the inverse of P. And Alice publishes the value of N and P and keeps the value of A secretly. So if Alice wants to send message X in Zn, and then Alice can compute the signature Y, that is X to the power of A modulo N. And Alice send the sent message X and Y. X is the message, and Y is the senator to Bob. Okay. After Bob receive the sent message X and Y, and then by the public key of Alice, and then Bob conducts a verification process by computing Y to the power of B modulo N. So that is here is the verification process. If X is congruent to Y to the power of P modulo N, then the verification is true. And if not, then the verification is false. But in practice, we use the hash value of the message instead of X for the signing process. So in practice, we send the message X, the hash value of X, and the signature. Okay. Any questions? If
No.
no, I think uh, we have a break, 10 minutes, okay?
Okay. So
Okay.
we'll back at 10:15.
10:15, yeah.
Okay.
Okay, thank you.
Halo, Pak Zaki. Pak Zaki. Halo, Pak Zaki.
Halo.
Okay.
Ya,
So, can we start now?
oke. We start now.
Okay.
Oke. Okay. After we discuss about the RSA crypto system, now we discuss about the algorithm public key crypto system or asymmetric crypto system. So in 1955, the Tahir Al-Jamal published a paper. The title is Public Key Crypto System and a signature scheme based on discrete logarithm. And actually, he used the same uh, hard problem with Diffie-Hellman key exchange. So Jamal used the discrete logarithm problem to construct a new public key crypto system. Okay. So the first process is key generation. Suppose that Alice wants to send a plain text to Bob. So Bob create uh, a pair of keys, the public key and the private key. In here, Bob choose a prime number P, a big prime number P, and G as the primitive root modulo P. And then Bob choose an integer E and computes P is equal to G to the power of A modulo P. And then Bob published the public key that is P, the value of the three values, it is P, G, and B, and gives A secret. So A is the private key. And the second process is encryption conducted by Alice. Okay, Alice knows the public key from Bob, that is P, G, and B, and then Alice chooses a plain text M, and Alice selects a random integer K, and then Alice encrypts the plain text M by computing two values, y1 and y2. Y1 is G to the power of K modulo P, and y2 is M P to the power of K modulo P. Alice sends the ciphertext, that is two values, uh, y1 and y2, to Bob. And the third process is decryption conducted by Bob. So in here, Bob receives the ciphertext y1 and y2 from Alice, and Bob, he has the secret key or the private key, that is A, And then Bob decrypt the ciphertext by computing Y2 and Y1A inverse modulo P. And here's the proof of the decryption function that this works. Okay. The proof is also very simple. So in here, every encryption, Alice selects a random integer k. So different with the RSA crypto system, the El-Kamal crypto system are random. Okay, the El-Kamal crypto system is a randomized crypto system. It is every ciphertext, every plaintext can be encrypted into different ciphertext because every encryption at least lacks a random integer. But uh, the disadvantage of the El-Kamal is the size of the ciphertext is 2 times bigger than the plaintext. So the ciphertext of the El-Kamal is 2 times bigger than, yeah. But the advantage of the El-Kamal system is the randomized properties of the ciphertext. Okay. And we can also generalize the El-Kamal system into a finite cyclic group T. It is generalization, the generalization of the El-Kamal system. You can use arbitrary cyclic group T. Okay. Okay, this is the encryption and also the decryption. And we can also use the same cyclic group which are used by which is used by the development exchange. And also we also if you already know the elliptic curve cryptography or elliptic curve yesterday, and we can also use the elliptic curve for development and El-Kamal crypto system. Okay. And same with the RSA ecosystem, the El-Kamal crypto system uh, can be modified into a digital signature, and the digital signature scheme is given below like this. So Alice wants to send a message into Bob, and Alice wants to sign her message. So Alice create the public key and the private key. The first one is Alice secretly choose a lot prime number P, and then a primitive root modulo P, that is G, an integer A, and then Alice compute P is to the power of A modulo P, and then the public key is the value of P, G, and P, and the secret key is the value of A. Suppose that Alice has a message X, and then Alice computes the signature of X by randomly select an integer K such that the K is relatively prime with P minus 1. And then Alice compute two values, y1 and y2. Y1 is g to the power of k modulo p, and the y2 is x minus a y1 times k, the inverse of k modulo p minus 1. And then Alice sends the message x with the signature y1, y2. And then Bob receive the signed message that is x, y1, and y2. And Bob also knows the public key of from Alice that is P, G, and P. And then Bob uh, conducting a verification. The verification is true if this equation or this congruence is true. Okay, and it you can prove it that it is true. Okay, and actually the El digital signatures are still used today. Uh, if uh, if for the public encryption, we use DSA, RSA. For the encryption, for the digital signature, digital signature algorithm, uh, the international standard is using the DSA, or digital signature algorithm. The DSA is actually the El-Gamal digital signatures using the SHA hash function. And now, uh, on the internet, many many use the ETDSA, or elliptic curve digital signature algorithm. Okay, and now we will discuss about the elliptic curve cryptography, or ECC. I think the someone of you is already know the elliptic curve because yesterday the topic of the training session is about elliptic curve. So elliptic curve uh, is a very famous topic in number theory, but in 1985, there are two people, Neil Koplit and Victor Miller, proposed a new kind of group that can be used for development exchange and also for El-Kamal public key crypto system. So Neil Koplit and Victor Miller use they use both of them use elliptic curve group defined of a finite field, and this is known as the ECC, or elliptic curve cryptography. Before we start about the elliptic curve cryptography of a finite field, uh, to understand how the operation on an elliptic curve is works. So First, we give the definition of an elliptic curve over the field R, the set of all real numbers, or the real field. Okay, let A and B are real numbers such that the 4a cubed plus 27b squared is not equal to 0. It is, we call it the discriminant. Then a non-singular elliptic curve E is the set of all points x, y, such that the equation y squared equal to x cubed plus ix plus b is held together with a point O that called the point at infinity. So this is the elliptic curve, the set of E. This is the example of an elliptic curve y squared equal to x cubed minus 4x. You can plot it using like a GeoGebra or MATLAB or Maple or something else. And the interesting one is that the operation is goes like that, like this. Uh, there are three conditions. If we have 2 points like this means that x1, if x1 y1, x2 y2, if they are different, then uh, the operation between 2 points that we call it addition is performed like this. We make a line through that 2 points, and then the line will uh, cut to another points on analytic curve, and then reflecting on the x-ropes, and we have the result that is the addition of that 2 points. And if uh, x1 is equal to x2, and then the line that two line can never be crossing the elliptic curve. So we define that the addition of that curve is the point at infinity. And and the third condition, if we want to add s- the same points, then we make a slope line, and then the line will intersect to another point on E, and then we reflect, and we get the addition of the same point. And here we now move to the elliptic curve of the finite field. In here we use the finite field ZP. Let P be a prime number bigger than 3. The elliptic curve EP is the set of all points xy in ZP that satisfies this congruence y square congruent to x cube plus ix plus p modulo p, where I and p is in CP, such that 4a cube plus 27p square is not congruent to 0 modulo p. And to get,
Zaki,
yeah,
can I ask something?
yes.
Uh, why in some references they use the discriminant of the elliptic multiply by minus 16? Uh,
Minus 16.
yeah, some references use minus 16 uh, multiply by 4a cubed plus 27b squared.
Oh, it's for also for prime p bigger than 3.
Hmm? Sorry?
The prime is also bigger than 3, or the
The
prime.
prime?
Ah,
Yeah, the prime is still bigger than 3. Yeah.
maybe from the discriminant, I think. I don't know. I don't.
Okay, okay.
Maybe
Thank
you
you.
can ask Bu Anissa.
Yeah,
Yeah,
I
yeah,
forgot asked to her
yeah,
2 days
yeah,
ago.
yeah. You should ask Bu Anissa.
Okay,
Yeah,
okay.
yeah. Sorry.
So, but okay, why we should choose the prime number bigger than 3?
Actually, we also can use 2, 3. It depend on the discriminant.
Oh,
Yeah.
oh, okay, okay. Ah, okay, thank you.
I think is about the characteristic of the field. Okay, and here's the addition operation on the elliptic curve FDP. There are three conditions. It's given like this. Lambda is the okay. There are three conditions. If we have 2 points P and Q, P is x1, y1, and Q is x2, y2. And then if x1 is equal to x2 and y1 is minus y1, wait, sorry, y2 is equal to minus y1, and then P plus Q is defined point at infinity. Otherwise, suppose that P plus Q are x3, y3, then x3 and y3 is given like that, where the value of the lambda is different. If okay, something like that. And we have uh, some properties that uh, the point at infinity is the identity element, and and we can prove that the elliptic curve is a finite abelian curve, even though that the proof of the associative properties are very difficult. Yeah, and here is the uh, a method if we want to find all of the points on elliptic curve. In here, we use an example. Let E be an elliptic curve defined by an equation by square is equal to x cubed plus x plus 6. modulo 11. And first, we list all of the on element of Z11, 102 until 10, and we compute uh, x cubed plus x plus x 6 modulo 11 from x 0 until 10, and we get these values. And after that, we check that uh, the values is value is a quadratic residu or not. Quadratic residu is mean that an element in Z11 has a root, has a square root. Okay, 6 is no, x no, 5 yes, because uh, 4 square is 4 square is 5, and 7 square is also 5. And for 3 is also a quadratic residu because 5 square is 3 and 6 square also 3. And here, so from this computation, we know that the elliptic curve has 13 points. The first one is, of course, the point at infinity, and then 2, 4, and then 2, 7, and then 3, 5, 3, 6, and so on. Okay, this is very simple. And I give exercise to compute all of the points on an elliptic curve. And here's an example of addition on an elliptic curve. We use the same elliptic curve from the previous example. And let P on a point 2, 7, and we will compute the values of 2P, that is P plus P. Since x1 is equal to x2 and y1 is equal to y2, then the value of lambda is computed like that. And we get the value of lambda is 8. And we obtain the value of x3 and y3 like that. So we have 2p is p plus p is the 0.52. And now we want to compute 3p. We can compute this by p plus 2p or 2p plus p or p plus p plus p. Okay. In this example, we want to compute 5,2 plus 2,7. Okay, since x1 is not equal to x2 and y1 is not equal to y2, then the value of lambda is like this, different with the previous one. So the value of lambda is 2, and we obtain the value of x3 and y3 is 8 and 3. So the, the point 3p is 8, 3. Okay, and now in the elliptic curve discrete logarithm problem. Okay, let P be a point on E and an integer n between 1 and the order of P. Okay, let NP is P at plus P as many as n, and let Q is equal to NP. Then the discrete logarithm problem is the problem of determining the value of n when only P and Q are known. So okay, that is the discrete logarithm problem on elliptic curve, or we call it elliptic curve discrete logarithm problem, or ECTLP. Okay, and then we can uh, construct an elliptic curve development exchange, or ECDHE, by using like a cyclic subgroup of an elliptic curve. So here, Alice and Bob agree on elliptic curve E and a point P on an elliptic curve. And then Alice secretly choose an integer A and then compute the shared key as A, that is AP. And then Alice sends the shared key as A to Bob. On the other side, Bob secretly choose an integer B, and then Bob computes SP, that is PP, and then Bob sends the shared key SP into Alice. So in here, Alice uh, has the shared key from Bob, that is SP, and Bob also knows the shared key from Alice, that is SA. Then Alice compute key A, that is ASP, and Bob computes KB, that is PSA. In here, we have that the key A is equal to KB. Yeah, you can prove it. It is very simple. Therefore, Alice and Bob agree on the same key, that is key A equal to KB. Actually, now the ETDSI, that is elliptic curve Diffie-Hellman exchange, now is used widely on the internet. For the example is uh, WhatsApp application that we use every day. WhatsApp use very famous elliptic curve, that is curve 25519. Uh, okay, and the encryption that use is the AES 256 bit. And now we move to the Elgamal elliptic curve crypto system, or K generation. Okay. Since we can construct a cyclic subgroup of an elliptic curve, so we can apply this to the Elgamal crypto system. So here, the Elgamal elliptic curve crypto system. Suppose that Alice wants to send a secret message to Bob. So Bob has to make a pair of keys, that is public keys and the private key. In here, Bob choose prime number P and AP in CP, such that the determinant is not equal to 0. And then Bob choose a point P on an elliptic curve. And then Bob secretly choose an integer R and computes Q equal to RP, and publish the public key KP, that is the elliptic curve EP, and then the point P and the point Q, and keeps the value of R. So the R is the private key. Okay, Alice knows the Bob's public key, that is Kp, the elliptic curve, and then the point P and the point Q. And then Alice choose a plain text that is a point M in the elliptic curve. And then Alice randomly selects an integer K, and then Alice uh, encrypt the plain text M by computing two values, that y1 and y2. The y1 is kp and the y2 is m plus kq. And then Alice sends the ciphertext y1, y2 into Bob. Okay, after that, Bob receives the ciphertext y1, y2 from Alice, and Bob also know the private key, that is R, and then Bob decrypt the ciphertext using the private key R by computing y2 minus R y1. So, okay, okay. On the development of elliptic curve cryptography, now is widely used on the internet for hardware application. Uh, the elliptic curve are defined of a binary field, and now the digital signature standard are based on the ACDSA elliptic curve digital signal algorithm, and elliptic curve has advantage over the RSA photo system because the elliptic curve cryptography requiring a shorter key length than RSA for the same level of security. And also, elliptic cryptography now used widely on the TLS or transport layer system, security protocol, and also in the cryptocurrency. But the security of the elliptic curve is also based on the discrete logarithm problem. Okay, it is some of the application of the ACC on the smart card. And here are some of the advanced topic on the elliptic curve cryptography. There are many topics like Mrs. Alisa that and Winda. Maybe from the yesterday's lecture, uh, Bu Alisa talk about pairing on elliptic curve. I don't know. Also isogeny. Yeah. But I'm not work on this area. Okay. Okay. In 1993, Peter Shor published a paper that is it's like the end of the encryption, not the public encryption. The title of the paper is Polynomial Time Algorithm for Prime Factorization and Discrete Logarithm on a Computer Quantum. Uh, this paper said that if a quantum computer is successfully realized on the on the big scale, I think. Then the factorization and discrete algorithm problem could and be easily solved. The meaning of polynomial time is the same as the easy to solve. So after that, uh, there are new term in cryptography or new kind research in cryptography that is called post-quantum cryptography or PQC. So the cryptographic system that's based on factorization problem and also discrete logarithm problem, the RSA system, Gamal system, elliptic curve cryptography will be no longer secure if a quantum computer with a large scale are realized in the future. For now, the RSA, the Gamal, and elliptic curve are still safe to use for data security, but with the longer key. And therefore, many researchers in cryptography try to find the another cryptographic system that are resistant to counter quantum attack. Okay. And for post-quantum cryptography candidates, there are many hard problems that can use. The first one and the famous one is the lattice-based cryptography, which is based on the hard problem in lattice, such as the shortest vector problem. And some years ago, the NST standard uh, told the winner of the competition. The name of the winner is Crystal Kuiper Crypto System, and it will become our new standard. And the other system is the anti-RO. I think that Mas Ali know it very well. And there are also code-based cryptography, crypto system that the security is based on the hard problem on coding theory, like the Nicholas crypto system is based on the decoding problem on a linear code. Naturally, Nicholas system is found in 1978 and still uh, very hard to break, even we use the quantum computer. But there are some issues on the keys that is still need very big key. And there are also multivariate cryptography. The security is based on the hard problem that is finding solution to system multivariate equation of a finite field. The example is the HFE crypto system, the MI Matsumoto Imai crypto system. And there are also many hard problem like maybe hash-based cryptography and isogeny and also non-commutative cryptography. The security is based on the problem on non-commutative object vector. Okay, I think that is Mas Ali uh, for sharing session today. Uh, if we
Okay,
want to, yeah,
okay. Thank you, Pak Zaki, for your presentation. Maybe from the participants, is there any questions for Pak Zaki? for the lecture? Anyone? Okay, it's clear. Thank you. Uh, so at the in the end of the presentation, uh you you say that some post quantum cryptography crypto system, right,
Yeah.
Zaki? Uh, I just want to know for your work today, which one you?
Me, I will code-based cryptography.
Oh,
Yeah, I
so
work in
you
code-based
still on
cryptography.
campus.
No, yeah.
Before,
You-
I forgot. I forget. Maybe last year you say that you try to learn about the isogeny-based cryptography.
No, no, no.
Oh,
It's it's so hard for me. Oh, yeah, yeah. No, I
uh,
changed.
so if there is no question, maybe we can end the session here, and we will continue at 1 p.m. for the exercise session. Oh, maybe Pazaki, do you have the problem set for the exercise?
Yes.
Ah, yeah.
I think Mas Adi Sudrajat that will conduct the exercise session. Uh,
Ah,
yeah, yeah. Or I
so
send it to the chat.
you send the chat.
Can you share it? Share
Okay.
the exercise
Yeah.
in the.
Maybe maybe you can share the slide,
Okay.
also the slide, so the participant can
Okay.
learn from it to
Yeah.
try the exercise by themselves.
Okay. Wait a minute.
Okay. Okay. Thank you, Adi. Mas Adi.
Loh,
Mas Adi share the exercise. So for everyone, you can download it and mm, let me see. Okay, I think I can open the exercise. Okay, so the exercise and the materials uh, already uh, shared in the chat column. You can download it and try the exercise before the exercise session. Uh, I see it the exercise actually uh, there is no custom cryptography problem, so uh, the
hmm.
problem is maybe easier than you think.
Yes.
So you can
It is.
try it.
Yeah.
And is are we allowed to use some program,
Yeah. Yeah.
Sage or
Sage.
Pari,
Yeah. Yeah.
Magma?
Yeah.
So
Good.
for everyone, uh, you can try it. Use some program, Python maybe, or SageMath or Magma, to solve the problem that already shared. Okay. Okay. Hmm. Once again, thank you, Ms. Zaki, for your presentation. Uh, and for today's session, for the presentation, I will stop here. And you have 5 minutes to download before I end the Zoom meeting. So thank you, Pak Zaki,
Oke,
and
thank you
see
Pak
you
Fahri.
everyone at 1 p.m.
Oke.